Cantilever slab of effective span 1 meter carries superimposed load of 1.5 kN per meter square, including floor finish. Full stop. Calculate the depth and area of reinforcement. Full stop. Use M20 concrete and mild steel. Take modification factor, it is 1.55. Okay. So first of all, write down the given data for this. Given data. So first of all, effective span it is given. LE is equal to 1 meter it is given. Then live load including floor finishing it is given 1.5 kilonewton per meter square. 1.5 kilonewton per meter square. This one it is given. Okay. Then use M20 and mild steel. Use M20, that is FCK it is equal to 20 Newton per mm square. FCK is equal to 20 Newton per mm square. And FY it is given mild steel. That is means FY is equal to 250 Newton per mm square. So mild steel means it is yield strength it is 250 Newton per mm square. This data it is given. So step number 1 for design of cantilever slab. Step 1, trial depth of slab. Trial depth small d is equal to span divided by span divided by 7 into modification factor. So span it is 1 meter, means that is 1000 mm. 1000 mm divided by 7 into modification factor, it is 1.55. Okay, we'll get the effective depth. It's small d is equal to 1000 divided by 7 into 1.55. It will be 92.165 mm. So round the figure will take it is 100 mm. This one it is small d. Okay. So now we need to calculate the overall depth. Capital plus cover plus diameter of bar means 5 by 2 means 5 by 2 means 5 by 2 means 5 by 2. Okay. So just assume cover cover is equal to 15 mm. Assume cover is equal to 15 mm and diameter of bar it is take 10 mm. Okay. So overall depth d is equal to small d it is 100 mm plus cover it is 15 mm. Plus diameter of bar we just assumed it is 10 mm, means it is 5 mm. 5 by 2 it is 5 mm. So overall depth is equal to 100 plus 15 plus 5, it is 120 mm. So this one it is overall depth of slab. It will be capital D is equal to 120 mm. Capital D is equal to 120 mm. Okay. So now step number 2, effective span. Step number 2, effective span. Okay. Actually here it is given directly effective span. LE is equal to 1 meter. It is directly given. If it is not given, so if it is beam slab, it is simply supported. Then LE is equal to L plus center to center distance between two supports. That is we call it effective span. But here it is our slab. It is cantilever slab. So one end it is fixed, other end it is free. So LE is equal to it is 1 meter. It is directly given here. Okay. So next step number 3. Step number 3, load calculation. Step number 3, load calculation per meter. Load calculation per meter. Load calculation per meter. Load calculation per meter. Okay. So first of all, calculate dead load. First it is dead load. Dead load is equal to dead load. Dead load. It is overall depth of slab. It is 120 mm into per meter 1 into unit weight of concrete. It is 25. So overall depth of slab it is 120 mm. Convert it is in meter. 120 into 1 into unit weight of concrete. It is 25. So dead load is equal to, we will get the dead load 0.120 into 1 into 25. It will be 3 kilonewton per meter. 3 kilonewton per meter. Okay. So second, lie load it is given. Lie load including floor finishing. Lie load including floor finish it is given 1.5 kilonewton per meter square. So for 1 meter we are considering, that's why it is multiplied by 1. It will be 1.5 kilonewton per meter. Okay. So total load on slab now. Total load on slab. Total load, that is W is equal to dead load plus lie load. Dead load plus lie load including floor finish. Lie load it is given actually including floor finish. That is mean 3 plus 1.5. 3 plus 1.5. So it will be 4.5 kilonewton meter. 4.5 kilonewton per meter. 4.5 kilonewton per meter. Now factored load. Factored load is equal to W into 1.5. W into 1.5. So 4.5 into 4.5 into 1.5. So is equal to 4.5 into 1.5. So factor load it is 6.75. 6.75 kilonewton per meter. Okay. Step number 3, factored bending moment. Factored moment. Step number 3. Factored moment. So factored moment mu is equal to when slab it is cantilever. So for that W into LE square divided by 8. LE square divided by 2. The slab it is cantilever. That's why WL square by 2. Okay. So is equal to WU it is 6.75 into 1 square divided by 2. So this one it will be factored movement. So it will be get mu is equal to 6.75 into 1 square divided by 2. It will be 3.375 kilonewton meter. 3.375 kilonewton meter. Okay. So now step number 4, check for depth. Step 4, check for depth. Check for depth. So actual depth we are calculated in step number 1. So just check it is okay or not. Okay. So for that we need to equate mu is equal to mu limiting. Okay. So mu it is 3.375 into 10 raised to the power 6 Newton mm. Mu limiting. So grade of steel it is Fe250. For that mu limiting for that 0.149 FCK into BD square. FCK into B into D square. Okay. So D into B into D square. Here it is, put all this value here. Unknown it is D. So mu again, mu 3.375 into 10 raised to the 6 is equal to mu limiting 0.149 into FCK it is 20. FCK it is 20. B it is we are considering for per meter. It is 1000 mm into D square. D it is just calculate the D if it could have. Okay. This is required. We'll get the this way. It is required. Small d. So now 3.375 into 10 raised to the 6 divided by 0.149 FCK is 20 into 1000. Okay. We'll get D is equal to 33.65. 33.65 m. The actual we are provided it is small d it is 100 mm. So this one it is less than 100 mm. So it is okay and safe. It is okay and safe. So this one it is okay and safe. Okay and safe. So this one it is, we just check the slab it is depth provided it is okay or not. Okay. So then next step, area of main steel. Step number 5, area of main steel. Step number 5, area of main steel. Area of main steel. Area of main steel. AST is equal to formula. AST is equal to 0.5 into FCK. 0.5 into FCK divided by Fy in bracket 1 minus root of 1 minus 4.6 mu divided by 4.6 mu divided by FCK BD square. FCK BD square. FCK BD square. FCK BD square. Okay, BD square. Bracket close B into D. Bracket close B into D. Okay, close B into D. Okay, put all this value here. 0.5 into FCK is 20 divided by Fy it is 250. Fy it is 250. Bracket close. 1 minus root of 1 minus 4.6 into mu it is 3.375 into 10 raised to the power 6 divided by FCK BD square. FCK it is again grade of concrete it is M20, that means 20 into B it is 1000, B into 1000, D it is 100 square, 100 square, 100 square divided by B into D, into B into D, B into D, into B into D, into 1000 into 100. It will be get AST value on this. So AST is equal to, so just calculate this one. AST is equal to, AST is equal to, we get this value 154.4 m, 154.8 m, 154.8 m, 158.4 mm square. Okay. Mm square. Now AST minimum for this number one, for this AST we are calculated number one. So AST minimum still it is how much it will be required, okay, for FP 250 grade of steel. So AST minimum, now calculate the AST minimum. Just second. AST minimum is equal to 0.15% of 0.15% of B into D, 0.1% of B into capital D. Okay, so that is equal to means, that is means 0.15 by 100 into B it is 1000. Overall depth of slab it is, overall depth of slab it is, overall depth of slab it is 120 m. It will be get AST minimum. Okay. So minimum still it is that. Okay. So 0.15 by 100, 0.15 by 100 into 1000 into 120, 1000 into 120. So it will be 180 mm square. So AST minimum it is 180 mm square, 180 mm. Actually AST it is by formula using, it will be get 150. So AST minimum is equal to AST now. So AST is equal to, AST is equal to AST minimum, AST minimum is equal to, it is 180 mm square, 180 mm square, 180 mm square, 180 mm square. Okay. So now we are providing AST it is 180 mm. Okay. So spacing now, calculate the spacing, spacing for main reinforcement, main reinforcement 8 mm diameter of bar, main reinforcement 8 mm diameter of bar, diameter of bar, 8 mm diameter of bar. Okay, spacing for main reinforcement 8 mm diameter of bar. Okay, spacing or spacing of reinforcement, spacing of reinforcement for 8 mm diameter of bar, 8 mm diameter of bar, 8 mm diameter of bar. The spacing formula, there are three conditions. First, in that spacing is equal to 1000 into A5 by 8, 1000 into A5 by 8. A5 is area of one bar, area of one bar, one plate, that is 8 mm square. A5 by 8, A5 by 8. A5 by AST is equal to 1000 into A5 it is 5 by 4 into 8 square into 8 square divided by AST. AST it is 180 mm. AST it is 180 mm. This one it is spacing 1. 1000 into 5 by 4 into 8 square divided by 180. It will be 279.25. 279.25 mm. So round the figure it will take 270 mm center to center. 270 mm center. So spacing second formula it is spacing 2. So there are three conditions. Spacing is equal to 3D. It is 3 into depth it is effective depth it is 100 mm. So it will be 300 mm. Third one it is spacing 3. Spacing is equal to 300 mm. So whichever is less from first second, that is we provide the spacing. So which one it is less? It is first one, 270 mm center. So provide main steel of 8 mm diameter at 270 mm center to center. 270 mm center to center. Okay. So this one it is main steel. Now next step number 7, distribution steel. 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 Okay. Distribution steel it is ASTD is equal to 0.15 by 100 into B into D. 0.51% B into capital D. Okay. So distribution steel it is, that's why Fe 250 grade of steel, that's why it is 0.15%. So is equal to 0.15 divided by 100 into B it is 1000 mm and D it is 120 mm. So ASTD is equal to again it is 180 mm square. ASTD is equal to again 120 mm. ASTD is equal to again it is 120 mm. ASTD is equal to 180 mm square. 180 mm square. ASTD is 180 mm square. Okay. Now spacing for that. Here it is also there are three conditions for spacing. Now spacing. So for first spacing it is formula spacing is equal to same here. Spacing is equal to 1000 into A5 by AST. 1000 into A5 by AST. A5 by AST. 1000 into A5 by AST. Here it is ASTD. area of distribution steel. Thousand into Fi it is pi by 4 into 6 square. Just assume distribution steel it is reinforcement it is 6 mm diameter. Okay, so pi by 4 into 6 square divided by STD it is 180 into 1000. So it will be 157 mm. 1000. It will be pi by 4 into 6 square. 6 square. We are just assume the reinforcement in distribution side it is 6 mm diameter. Okay. So STD it is 180 mm. STD it is 180 mm square. 180 mm square. Spacing for that is equal to 157.07. So round the figure we take it is 150 mm center to center. 150 mm center to center. This one it is spacing 1. Okay. So it will be first. Second, for distribution steel it is second. For second it is 5D. Okay, so 5 into 120. 5 into 120. 5 into 120. It will be 600 mm. 600 mm. It is 600 mm. 600 mm. Then third one it is spacing is equal to spacing is equal to it is 450 mm. 450 mm. So which one it is less from out of three? First, provide 6 mm diameter at 150 mm center to center. 150 mm center to center. 150 mm center to center. So this one for distribution steel. Okay. So this one it is completed. Design of cantilever slab. Okay. Design of cantilever slab.